everyone. It's Wednesday, and it seems like this live stream has been a long time coming. I had to go back and review all of my examples and make sure I remember them. So, anyway, this week we are going to be doing our oxidation states and then balancing redox equations, which I had hoped to do several weeks ago. Anyway, just making sure with OG benchmarks that my volume is all right. It looks like the internet is okay. I have no kid events to take kids to today, so I think we are all set. If you have questions, please just put them in the chat, and I'll try to keep an eye on that and make sure that I answer questions. And okay, great. Yes, audio's fantastic. That's great. So let's just go ahead and get started here. All right. So the first thing I want to start with are assigning oxidation states, which means we have to start with the rules for assigning oxidation states. So let's just quickly go through the rules. And you can see I've got a bunch of examples down at the bottom of the screen, and so we'll do some practicing. Okay, so rule number 1 here is the oxidation state of an atom, and its elemental form is 0. Now, the one thing I want to point out here is some of the elements have elemental forms that are not just the atom. So for example, sodium is a metal, and its elemental form is just written as sodium Na. Like, that's it. That's very easy. But something like hydrogen, in its elemental form, is not just H, but it's diatomic, which means it's H2. So that is H2 is hydrogen in its elemental form. Again, it's a diatomic gas. The same is true with like nitrogen, oxygen, fluorine, chlorine, all of these guys. Oops, that should have a 2. Sorry, I got a little too happy with the writing. They're just a handful. This is not an exhaustive list, by the way. They're just a handful of these that are diatomics. Some teachers or professors want you to have these memorized, others don't, but just as an FYI, so you know, most elements in their elemental form will just be written as the symbol for the element, but there are a few here that are diatomic, meaning that there are 2 atoms bonded together in the elemental form. Okay, so let's go on to rule number 2. The oxidation state of a monoatomic ion is its charge. So I'm going to pick on sodium again. Sodium, when it is an ion, has a +1 charge. So +1 is also its oxidation state. Oxygen, when it is an ion, has a -2 charge. So that is also its oxidation state. So when you have a monoatomic ion, this is not a polyatomic, this is a monoatomic ion, its charge is its oxidation state. All right, rule number 3. The oxidation state of hydrogen in covalent compounds. Just want to make sure covalent compounds is +1, although just as an aside, you see this in ionic compounds mostly too. But then it's a monoatomic ion. So as we do our covalent compounds and we're trying to figure out oxidation states, we're going to assign hydrogen an oxidation state of +1. This really ties into rule number 4. So for oxygen, again, in covalent compounds, we're going to give it an oxidation state of -2. There is one exception to this, and that is the peroxides, the most common being hydrogen peroxide. And in that case, the oxidation state for oxygen is actually -1, and hydrogen is +1 there as well. Okay, so oxygens are almost always going to be -2 unless you happen to have a peroxide, which honestly you don't run across that often. Okay, rule number 5. In binary compounds, these are compounds where 2 elements are bonded together. So this doesn't necessarily mean that it is 2 atoms, but 2 elements. So you can have more than 1 atom, but as long as you don't have more than 1 element. Anyway, so in binary compounds, the electronegative atom is assigned a negative oxidation state, and that is equal to its charge in ionic compounds. So again, we will see this in the practice, but if you're trying to decide, oh wait, I've got these 2 elements, which one do I give the negative oxidation state to? Go with the one that's more electronegative. Okay, and finally, rule number 6, we'll use this one quite often actually, is the sum of the oxidation states for a neutral compound must equal 0. And the sum of the oxidation states for an ion must equal the overall charge on the ion. So this is a rule that we will use not only with compounds that are neutral, but when we're trying to determine oxidation states for, say, a polyatomic ion, we are going to use this rule as well, except in that case, our oxidation state is going to equal the charge on the polyatomic ion. Again, these are the rules, but they're going to make more sense once we put them into practice. So let's work some examples. Okay, good. And it looks like there are no questions so far, which is good. The rules are the rules, but really it's all in the practice that makes the difference, I think. All right, so for my first example, I have carbon monoxide. So I'm going to use my rule for oxygens and covalent compounds. Oxygen, I'm going to assign a -2 oxidation state. And this is a neutral compound, meaning there's no overall charge. So that means the oxidation state on carbon must be +2, because then the sum of these oxidation states equals 0. That's exactly what I want. So you can see how we're already starting to apply the sum of the oxidation states. And here we've got oxygen, which is definitely our friend because we're always going to assign an oxidation state of -2, again, unless a peroxide. Okay, so let's go nitrogen monoxide. Again, oxygen, we're going to assign an oxidation state of -2. This is a neutral compound. All my oxidation states must add to give me 0, which means in this case, nitrogen is also +2. So you can see we've switched from carbon to nitrogen, but the oxidation state for these elements is actually the same in these respective compounds. Okay, but what if instead of having nitrogen monoxide, you have dinitrogen monoxide? So here we have N2O. Again, oxygen, we're going to say, is -2. And the sum of our oxidation states must equal 0, except we have 2 nitrogen. So if you want to think about this as an algebraic expression, it would be 2 times, I'm going to call it X, whatever the oxidation state is going to end up on nitrogen, plus the oxidation state on oxygen, which is -2, must equal 0. So you can see the difference between nitrogen monoxide and dinitrogen monoxide. You've got that element of 2 in there, which means the oxidation state on my nitrogen is 1+. And you can see if you substitute a 1 in here for your X, then you end up with a true algebraic expression. Okay, so let's switch it up. This time I have nitrogen dioxide, so I've got NO2, but I'm going to apply the same rules again. Oxygen is -2, but because I have 2 here, again, if I am writing an algebraic expression, I'm going to say nitrogen is X. I don't know what it is, but I'm going to add oxygen, but I have 2 of them. So there's a multiplier of 2 there, and again, that equals 0. So sometimes what I will do is I'll write a -2 there, but then above it, whoops, not a 2, I'll write a -4. Let's see if I can get that off, just as a reminder to me that I have 2 of them, and that's my multiplier. Again, kind of, you'll find you have your own style of how to organize these, and that's totally fine. Just find a way that works for you, that you can keep track of what's going on. So that means in this case, to make my algebraic expression here true, the oxidation state on nitrogen must be +4. Again, and you can see if you plug in +4 into this expression, you get a true algebraic expression. All right, now, okay, so this one, N2. I put it in as a trick because what did I write up here? N2 is nitrogen in its elemental form. That means the oxidation state here is 0. So I don't even have to do any math, no algebra. And that is the elemental form of nitrogen, so its oxidation state is 0. Okay, let's keep on moving. Hopefully these rules are starting to make sense. Again, there's some algebra to keep track of, and that's really the most difficult part for these, and then we'll do some with polyatomics. Okay, but let's do Li3N. Again, because we've got a binary compound, meaning we have lithium and nitrogen, we just have 2 elements. It doesn't matter that there are 3 lithium in here right now, it's still binary. I'm going to make sure that nitrogen it has the negative charge on it. It has the negative oxidation state, I should say. Now lithium, when it becomes an ion, what charge does it have? It has a +1 charge. And I have 3 of them. So again, if I write my algebraic expression here, I have 3 lithium. They have a charge of +1 plus whatever my nitrogen is must equal 0. And you can see how this works out so that nitrogen is going to get a negative oxidation state. It's going to get an oxidation state of -3, which is also its charge when it is a monoatomic ion. So you could have also thought about this as just an ionic compound, and given each of these are charges of their monoatomic ions as well. So it works out either way, which means I'll see students approach these kind of from different angles sometimes, and that's totally fine. As long as we both get to the same place in the end, it doesn't really matter. Okay, now let's do nickel oxide down here. So we need to figure out the oxidation state on nickel. Again, we're going to use our good old rule for oxygen, which means oxygen is -2. Now I have 2 oxygens, which means it's got a multiplier. So I am going to write -4 up here just as my reminder that my overall oxidation state here when I'm adding is actually a -4, which means my nickel must be +4 to give me a neutral compound. So by putting this -4 up here, it kind of gets around me having to write out a whole algebraic expression, but you can always write out a complete algebraic expression. That's totally fine. Again, find the way that makes the most sense to you and use that way. Okay, let's do our iron oxide. Again, finding the oxidation state. And this is something too that if you've done naming and you've tried to figure out going from the molecular formula to the name what Roman numeral you need, that is also finding the oxidation state on the metal as well. So this is repeating if you have already done your naming. Okay, so back to iron oxide, because I need to know what iron this is. Is this iron 2? Is this iron 10? Okay, so again, going back to oxygen, oxygen is going to be -2. I have 4 of them, so I'm going to write a -8 up here. All right, so that means iron in total must give me +8, but again, I have 2 of them, so that means the oxidation state on each iron is 4+. So hopefully that makes sense. It kind of gets around my algebraic expression, but I can write my algebraic expression if that is helpful. So I had 2 times whatever iron is, so we'll go back and say we didn't know what iron is, plus 4 times -2. That's my oxygen must equal 0. And so I just solved for x. Again, do the way that makes the most sense to you. So this would be iron 4. Oxide. I'm not sure if iron 4 oxide actually exists or not, but it doesn't matter because we're just doing an academic exercise here. Okay, let's go to what is this? P4O6. Again, same rule. So you can see a lot of these have oxygen in them. A lot of compounds have oxygen in them. And it's actually really helpful because as soon as we see oxygen in these covalent compounds, it's like, bam, oxygen is -2. Which is why what is that, rule number 4 is super helpful. Okay, so oxygen is -2, but I have 6 of them, which means I am going to have a -12 up here. So that means for phosphorus total, I must be +12, but I've got 4 of them. So that means each phosphorus is 3+. Again, I hope that makes sense. I will write down the algebraic expression that I did. So I have 4 times whatever phosphorus is, I call that x, plus 6 times -2. And of course that should equal 0 because we have a neutral compound, so our oxidation states must equal 0. Oh, good, Henry's here. Okay, hello, Henry. I thought I saw a chat pop up there. I wondered if there was a question. Okay, so let's go on to BRF3. This is kind of an unusual one here. So again, you might be deciding, well, which one do I give the negative oxidation state to? Well, you're going to give that to the most electronegative atom in the compound. In this case, that is going to be fluorine. So for fluorine, when fluorine is a monatomic ion, it has a charge of -1. Now we've got 3 of these, so that means overall I have -3 right here, which means bromine must equal +3, which I know feels really, really weird because we're used to seeing all of the halogens always be -1 all the time. But when we're doing oxidation state, it's not, for a monoatomic ion, the oxidation state is the charge. But really, and we'll see this when we do the redox equations, this is going to be a way for us to keep track of the electrons and to also help figure out elements that maybe are gaining electrons and then other elements that are losing electrons. So I don't want you to get too hung up on thinking that bromine has a charge of +3. Again, this is an oxidation state. It's actually a little bit different. We're just keeping track of electrons. Okay, let's go on to mercury chloride. Again, we're going to give the more electronegative atom the negative oxidation state. Chlorine, when it's a monoatomic ion, has a charge of -1. I have 2 of them. So this is going to be overall charge of -2. That means my mercury must overall give me a charge of +2. But because I have 2 of them, that means mercury is going to be +1. Again, if I write out my algebra, 2 to x plus 2 times -1 is equal to 0, and that's where I get the 1 on mercury. Okay, all right, so let's go on to some more practice with the oxidation states, because now I want to dive into compounds that have more than, well, some of these still just have 2 atoms, but the charged compounds and the compounds that have more than 2 elements in there. Okay, when does hydrogen have an oxidation number of -1? That's going to be really unusual, Henry. I don't know if I actually have an example where that happens. I'd have to think about that, but off the top of my head, I cannot think of a situation where hydrogen is going to have an oxidation state of -1. That's going to be quite unusual. I'm guessing that it exists somewhere, but again, off the top of my head, I couldn't think of an example where it would be -1. It's almost always +1. Oh, sodium hydroxide. Thank you, OG benchmarks. Let's see. No, sodium hydroxide you would still give, because hydroxide. Okay, OG benchmarks, I have to take issue with you. So hydroxide has an overall charge of -1, which means your oxygen is -2 and your hydrogen is still +1 for oxidation states. So oh, hydride, not hydroxide. Thank you. Yes, OG benchmarks, you're right. Hydride, not hydroxide. So sodium hydride. Sodium hydride is OG benchmarks. Yes, NaH. You're right. Sorry, I just read that as hydroxide because I'm ready to do polyatomic ions here. So you're right. You'd have the sodium as a +1 and the hydrogen as a -1. Thank you so much. See, this is why it's really helpful to have your moderator also be another chemist. Okay. All right. So now I kind of lost my train of thought. So polyatomic ions. Let's do some polyatomic ions. And then you can see at the bottom of the screen here, I've got some compounds that have more than more than 2 elements. Okay. So let's start though with sulfate, our sulfate polyatomic ion. So in this case, when I'm doing my oxidation states, they shouldn't add to give me 0. I want them to add to give me -2 because that is my overall charge on my polyatomic ion here. So again, I go to oxygen. Oxygen is going to be a -2. I've got 4 of them, so overall I'm looking at -8 for all of my oxygens. Now, for sulfur, again, I have to make sure this equals a -2. So I want my sulfur to not be a +8, but a +6. And again, I'll show you the algebra that I did. So sulfur, we don't know what it is, but I have 4 oxygens. They're each -2, and in this case, it equals -2. So that's why sulfur ends up as a +6, because I need an overall charge of -2. So that's what my oxidation state should also give me. Okay, let's do the same thing here with BiO3. Whoops, I meant to change colors here. Again, oxygen, -2. Oxygen is great for this. I have 3 of them, so overall I'm looking at, I'm going to squeeze that in, an overall oxidation state there of -6. For my bismuth, I don't want it to be +6 because that would give me an overall oxidation state of 0. This is not a neutral compound. It's got an overall charge of -1. So my bismuth is going to equal to 5+. Again, if I were to write out my algebra, it would be x plus 3 times -2 is equal to -1. All right, great. Okay, let's keep on rolling here. Hopefully these are getting a little bit easier. So we've got a cation here. So again, we want our overall charge to be +2. In this case, oxygen, good old oxygen, as -2. I have 2 of them. So overall, that gives me a -4. So in this case, again, I want my uranium to make sure to give more positive charge. So my overall positive charge is +2. So uranium, I want to be +6. I don't know if that really even made sense how I said that. But my algebra here is x, that's uranium, +2 times -2 is going to equal to +2. And that's how I figured out my x. Again, as you work through these, hopefully it just gets easier and easier. And I'm assuming you're already seeing the pattern with the oxygen. It's just always -2. It's always -2. Here we go. Here's oxygen again. It's -2. But that's what I want it to be. I want it to be just so routine it starts to get boring is ideally what I want it to do. Okay. So again, we're still working on some anions. Here we have nitrite. We've got oxygen again, which is -2. I have 2 of them. Oh, sorry, I was writing the multiplier instead of the final answer. That is 4. Again, my overall charge here, I kind of obscured it there, is -1. So my nitrogen is going to equal +3, and that'll give me an overall oxidation state of -1. You can see it's going to be not quite the same for nitrate because I have NO3 instead of NO2, but the idea is the same. Oxygen is -2. I have 3 of them. That's going to give me overall of 6 because I want -1. Then nitrogen here is going to be a +5. So you can see that even with very similar compounds, you can end up with different oxidation states for just depending on the different elements in there. How are we doing on time? Okay, I really feel like I want to do one of these polyatomics, and I want to make sure I save time to actually balance the redox. So let's do this sodium chromate. This isn't dichromate. This is chromate, sodium chromate. All right, so I've got 3 elements here. So how do I handle this? And there are a couple ways to think about this, but what I like to do is I like to break it apart into cation and anion. So what I actually do is I say, all right, my cation is sodium and my anion is chromate. My sodium as a monatomic ion has a charge of +1 and chromate has a charge of -2. Now, this means that sodium's already done. Its oxidation state is its charge because it's a monoatomic ion, so like you're totally set. And then I'm going to handle the chromate just like I did all of the ions that I did in the first row here. So oxygen, I'll switch colors, is -2. I have 4 of them, so that gives me -8. So for my chromium, I want the overall charge here to be +6, but I've got 2 of them, so that means on each, oh, sorry, that's carbon. This is oxalate, not dichromate, is 3+, although it doesn't really affect my math here. So the carbon, I have 2 of them. I don't know what it is. +4 times the oxygen gives me a -2 charge or -2 oxidation state. So that is how I handle larger compounds that have polyatomic ions. Is I'm going to break it apart into the cation and the anion and then figure out whatever I need to figure out. Now, usually, unless you have ammonium as the cation, usually what happens is the cation ends up being the monoatomic ion, so its charge is its oxidation state, and then you just have to work with whatever the polyatomic anion is. Okay, but it is almost 7:30, so I really want to go on to actually balancing some redox equations because we'll still get more practice with finding oxidation states in our redox equations. Okay, so here we go with balancing redox equations. So this is the half reaction method, which I like to use. Some of these redox equations you can actually balance by what they call inspection, by just looking at the oxidation states. But I find the half reaction method, I like it because it's very systematic, and that's just what I prefer. But I also know that the half reaction method is always going to work, no matter if the reaction is very simple and maybe I could balance it just by inspection, or if it's very complex and I have to do half reaction method. So I really prefer using the half reaction method just because it works with how my brain works, and I know that it's always going to work out. Okay, so let's quickly go through again the steps for the half reaction method, and then we'll work problems. And of course, when we're working problems, I will have the steps on the screen too and refer back to what the steps are. So our step one here, this is why we practice all this. We're going to assign oxidation states to all of the atoms in the reaction. Step two is we're going to identify the elements that are changing oxidation state. So we're going to have one element that is gaining electrons, this is our reduction, and the other element will be losing electrons, and this is our oxidation. So you're never going to have two elements that both lose electrons, because if you have a reduction, you have to have an oxidation. If you have an oxidation, you have to have a reduction. So in essence, you can think about electrons are leaving one element and then they must be gained by another element. So you're not just going to have all elements giving up electrons. Okay, so then our third step is we're going to write what are called the half reactions for our reduction and our oxidation. So we'll actually write a reaction that has electrons in it. We are going to balance each half reaction. Now this requires a couple of steps to balance each half reaction. So you can see we take a big reaction. We're going to basically split it into two parts. We're going to balance each part and then we're going to put it back together again. So for each half reaction, we're going to balance all elements except for oxygen and hydrogen. We're going to use water to balance oxygen, and we're going to use H plus to balance the hydrogen atoms. Then what we're going to do is we're going to add up charges on both reactant and product side, and we're going to add electrons to whichever side of the half reaction needs electrons. Again, this is something that's going to make more sense when we actually do an example. Okay, then once we have the half reactions balanced, we're going to try and put them together. But before we put half reactions together, they have to have equal numbers of electrons. Now, sometimes they automatically have equal numbers, and sometimes you maybe need to multiply one or the other, or sometimes both, by a whole number to get those electrons to be equal, because our electrons gained and our electrons lost must be equal. Then once we've got the electrons balanced, we're literally going to add the two half reactions together. A lot of species will cancel, they'll simplify. And at this point, we should have a balanced reaction in acidic solution. Now, you might also be asked to balance redox equations in basic solution. In that case, we're going to neutralize our H plus by adding hydroxide, and then we're just going to recheck to make sure everything is balanced. And again, we might need to do some simplification, but I'm going to go through both of these things. All right, hi Lionel. Oh, good. I'm glad you're here too. So let's get to actually balancing one of these, and we'll see how it all goes together. So you can see on this page, I have our list of steps that we need to take again so I can reference it back. And I just want to make sure, yes, okay. I wanted to make sure that my reaction was not hidden underneath my camera view here. So it looks like we're good. Okay, so our first step here is we're going to assign oxidation states to all of the atoms in this reaction. Now, the nice thing about this reaction is we have a lot of monoatomic ions, so their charge is their oxidation state. So really the only thing that I need to worry about is the MnO4, and to make sure I get oxidation states for that. Okay, so we have oxygen, which we all know and love, right? Because oxidation state of -2, I've got 4 of them, which gives me an overall oxidation state of -8. Now again, keep in mind it's got an overall charge here of -1. So my manganese is going to have a charge of +7. Okay, so now we want to identify the elements that are changing. Now in this one, I don't have that many elements to choose from, so it's kind of obvious, but still we'll mark it out. So you can see my manganese has gone from 7 to 2, +7 to +2, so manganese is changing, and iron is also changing because it's going from +2 to +3. So at this point, really, you just need to know the two elements that have changed. You don't necessarily, at this point, need to identify which one is reduction or which one is oxidation. You can, but you don't have to. You just want to know which ones are changing. So we'll just go from identifying those have changed, and let's not worry about identifying reduction or oxidation next. Let's write the half reactions, because I find that once I write the half reactions and I put the electrons in, then it becomes more obvious to me which one is reduction and which one is oxidation. But of course you can identify them here if you really want to. It's totally fine. Okay, so what we've got is we've got the manganese. So I'm going to have my MnO4 going to go to my manganese here. All right, so this is my half reaction for manganese. I'm only pulling out the species that have manganese in them. Okay, so then I'm following my rules here. Okay, write the half reaction. So I've got my half reaction. So let's balance this half reaction. So balance all elements except for oxygen and hydrogen. Well, that would be my manganese, so that's already balanced, so that's fine. Now I'm going to balance oxygen using water. So I have 4 oxygens here on the reactant side, and I have 0 oxygens on my product side. So I'm just going to add 4 waters here. All right, so my oxygens are balanced. My next step is I'm going to balance my hydrogens, and I'm going to use H plus for that. So again, I see I have 8 hydrogens on my product side. So I'm going to put in 8 H pluses on my reactant side. Okay, so now my hydrogens are balanced. Okay, and then part D here for step 4 is balance the charge by adding electrons to the appropriate side of the half reaction. So this is where I'm going to add up charges. Maybe I'll switch colors here. So on my reactant side, I have, this is +8, and this is 1 minus, so I have an overall charge here of 7 plus. And over on my product side, I only have manganese +2 that has any charge, so my overall charge here is 2 plus. So you can see that my charges on my reactant side and my product side are not balanced. Now, I can only add electrons, but I can add them to the reactant side or I can add them to the product side. And what I want is I want for my charges to be the same. A lot of times students get confused here and they try to make the charge 0. We don't have to make the charges 0. We just want them to be equal, but they can be any number as long as they're equal. So what I see here is that if I add electrons to the reactant side, I'm getting a little close here, and if I add 5 electrons, then that gives me a -5 charge. So if I have -5 plus 8 minus 1, that gives me not an overall charge of +7, but now this is an overall charge of 2 plus, so they are equal. So again, I didn't have to get them to 0. I just had to get them equal. So remember, when you're adding electrons, they have a negative charge, and it's only going to work to balance the charges to add electrons to one side or the other. So if you're adding electrons to the wrong side, you're going to find that your charges are going to go more and more unbalanced. So if you find that that is happening and you're getting stuck, try adding electrons to the other side. Okay, so that is our manganese half reaction. Now we have to write and balance our half reaction for our iron. So we have iron +2 going to iron +3. This is like the easiest one to balance ever. So again, but I'll go through the steps. So again, step 4, I'm balancing the half reaction. Balance all elements except for oxygen and hydrogen. Okay, that means ions must be balanced. They are balanced. Now we're balancing oxygen and hydrogen, but I don't even have any oxygen and hydrogen. So like the step 4B and 4C are totally moot because I don't have oxygen and I don't have hydrogen, so I don't even need to worry about it. So the only thing I need to do is balance my charge by adding electrons to the appropriate side. And yeah, I don't even need to do any kind of side calculations like I did with my manganese half reaction because I have a +2 oxidation state or charge on the reactant side and +3 on the product side. So all I need is 1 electron over here, and then of course 3 plus a -1 gives me +2, so like I'm totally set. So this one was actually really easy to balance and I didn't have to work nearly so hard. So those are the ones that we always like to see. Okay, at this point, sorry, I was almost about to skip this. At this point, I think it's easier to identify the reduction and the oxidation because it just makes more sense to me when I see the half reaction. So I can see in my top half reaction here, I have electrons on the reactant side. So this is the reduction. We also call this the oxidizing agent. And that means this half reaction here where my electrons are on my product side. This is my oxidation half reaction. and this is my reducing agent. So again, I just find it easier to identify these at this point in my half reactions and identifying it in my equations. But if you like to identify in your equations and you find that's easier, then absolutely 100% go for it. Okay, so at this point I have finished step 4, and I haven't finished step 5. I'm going to step 5. So I need to balance the number of electrons gained or lost. So you can see in my first half reaction, my manganese half reaction, I've got 5 electrons, but in my iron half reaction, I have 1 electron. So I have not yet exchanged the same number of electrons. I need to make these electrons the same. Again, this is pretty simple at this point because all I need to do is take my iron half reaction and multiply by 5, and then that will give me 5 electrons, and then my electrons are balanced. So what that's going to end up looking like if I just multiply this 5 on through is 5Fe2 plus goes to 5Fe3 plus 5 electrons. And you can see it doesn't unbalance my atoms, my number of atoms. They should still be balanced, and my charge should also still be balanced, which you can see, yes, my charge is also still balanced, except instead of being 2, it's now 10. Okay, now I want to add my half reactions together, and because I multiply through by 5, I'm just going to rewrite my manganese half reaction a little bit closer so it's easier to add in. So I'm just going to take this manganese half reaction and put it just right underneath here. Sometimes it's easier to rewrite after you've kind of worked these half reactions, not only so that it's neater, but so that it's easier to see anything that you maybe need to simplify or cross out. Okay, so literally I'm going to add these 2 reactions together. So I'm adding these 2 reactions together, and what you can see right off is my 5 electrons are canceling because they're on opposite sides of the arrow. So those are going to cancel. I don't have anything else, so a lot of times in both half reactions you end up with water and H+, so sometimes those will either cancel or they will simplify in some way, but for this one, it's just the electrons, and that's what you want. You want to make sure when you add your 2 half reactions, your electrons should always, always, always add out. If they are not adding out, then you need to go back to your individual half reactions and either make sure that they're balanced or make sure that you've got the same number of electrons in each half reaction. Okay, so that's all I'm going to cancel out, which means I just pull everything else down to get my balanced redox equation. So what I have is I have 8H plus my manganese oxide plus 5 Fe2 plus. Okay, so I think those are all my reactants. Now I go to products. So here's my 5Fe3 plus my manganese. Oh, I'm going to have to squeeze my 4 waters in. Okay, go right. Oh, that was close. Okay, so at this point, what you want to do is you want to make sure that your atoms are balanced and your charges are balanced. So if I'm looking at, we'll start with hydrogen. So I have 8 hydrogens on the reactant side, and yes, I've got 8 hydrogens on the product side. 1 manganese on the reactant side and 1 manganese on the product side. I have 4 oxygen over here, and yes, 4 times that is 4 oxygen. I have 5 iron and 5 iron, so my atoms are all balanced. Now I want to make sure that my charges add up, so I'm going to do a little what I call side calculation. I have a +8 from my 8 hydrogen, plus I've got just a -1 here, plus 10, 5 times +2, and this should equal 5 times 3, which is +15, plus 2, so this should be 7. Yeah, so I'm getting 17 equals 17. Sorry, these are both plus. So yes, that is balanced. So this is now a balanced redox equation. Okay, doesn't look like there are any questions. These always take longer than I think they do, but let's go ahead and do another one. I'll just get through as many of these as I possibly can. Okay, so we've got another redox equation, and we need to balance it. So again, we're going to start with step 1. We're going to work all the way through to step number 7. Okay, so I'm going to start with oxidation states. So starting with cyanide, nitrogen is more electronegative, so I'm going to give it its charge as the monoatomic ion of -3. Again, I've got an overall charge here of -1, so my carbon must be +2. I've already seen this manganese oxide, like I did this right there, so I think manganese was +7, yes. Okay. So I'm just going to steal my work from the previous problem. Okay, so now I have CNO. Again, here's my oxygen, yay, of -2. I'm going to give nitrogen a charge of -3 because it is more electronegative than carbon. This one is one of the ones that I think is a little bit tricky because after you've done oxygen, you do have to decide between carbon and nitrogen and what you're going to do there. All right, so we've got an overall charge of -1. So I've already got a -3 and a -2, which gives me -5. So carbon needs to be 4+. I know I'm kind of moving fast here, but I really want to get through the balancing of like this one and hopefully one more. And then I have manganese oxide right here. Again, oxygen is -2. I have 2, which gives me -4. So manganese is +4. Again, that's I know that's really, really, really fast there. You can always go back and double check my math and make sure that I've done everything right, but I really want to get to the balancing. Okay, so assign oxidative to identify elements that change oxidation state. So you can see carbon is going here from +2 to +4, so it's definitely changing. And again, my manganese here is also definitely changing. You can see my nitrogen stays at -3, so it is not changing. Nitrogen is something that often you will see change, but in this case, it's not changing. It's just the carbon and the manganese. So I'm going to just draw lines here just to bracket these guys to show, okay, here are my 2 elements that are changing. Again, I like to write my half reactions before I decide which one's being oxidized and which one's being reduced. Okay, I tend to move left to right, so let's start with the cyanide because why not? You can start with whatever half reaction you want. But I don't know. I just always tend to move left to right. That just always seems more comfortable to me. So here is my change in my carbon. So I pulled out my 2 compounds that had carbon that are changing, and I'm just going to ignore the rest because, again, we're taking a longer reaction and we're breaking it down into 2 parts. Okay, so that is my half reaction for carbon. So let's do step 4 here and go through our A, B, C, D. All right, so we're going to balance all elements except for oxygen and hydrogen, which means I need to balance my carbons and nitrogens, which are already balanced. So, like, that's easy. Balance oxygen using water. So I have 1 oxygen on the product side, so I only need 1 water molecule here on the reactant side. And then I'm going to balance hydrogen using H+. So I need 2 H+ on this side. And now I need to balance the charge by adding electrons to whichever side I need it. So let me do a little side calculation here. All right, so at least the reactant side is easy. This is just -1. And over here I have -1 plus 2. So that gives me a +1. That's supposed to be a plus there. The +1. All right, so again, it's not that the charges have to go to 0, they just have to be equal. And again, I need to add, I'm adding electrons. That's all I can do is just add electrons, but I can add it to whatever side that I want. So if I add 2 electrons over here, then I change my little side calculation, don't I? So then I have a -1 plus a +2, and now -2. And that gives me a -1. So now I've got charges that are equal on both sides. Yeah, they're not equal to 0. That's fine. They're just equal to each other, and that's what matters. Okay, so that is carbon taken care of. Let's do the manganese. All right, so I need the half reaction for manganese, so I'm pulling out my compounds or my species with manganese. And then this is MnO2, and that is neutral. Okay, again, I'm on step 4 here again with this half reaction. So balance all elements except for oxygen and hydrogen. So that would be manganese, and that's fine. It's already balanced. Balance oxygen using water. So I need to put 2 water molecules there to make sure my oxygens are balanced. and now balance hydrogen using H+. Okay, so I've got 4 hydrogen there, so I need 4H+ here. Okay, just double checking that all atoms are balanced. Great. So now I need to balance the charge by adding electrons to the appropriate side. So I'm going to do little half reactions right here, or half reactions, sorry, side calculations. I am working on half reactions. Okay, so this is going to be +4. My manganese here is -1. So this gives me a +3 overall. And then this is totally neutral. So, yeah, so this is not what I am actually going to have them equal 0. So at this point, because this is +3 right here, then what I'm going to do is I'm going to add 3 electrons. And then that changes my side calculation because then I have a -3 here. +4 -1 gives me 0. So cross that out. This now equals 0, and I've got 0 charge over here, so that's also 0. Okay, so now I've got, for this half reaction, it happens to equal 0, but again, my charges are equal on the reactant side and the product side. Okay, so that is step 4 done. Each of my half reactions are balanced. So now I need to go on to step 5. So I need to balance the number of electrons gained or lost in the half reactions. All right, so you can see in my top half reaction, I have 2 electrons, and in my bottom half reaction, I have 3 electrons. So I need to make these equal, which means I'm not going to just multiply one half reaction like I did in the previous problem. I need to multiply both of them. And so what I'm seeing is I want to make this equal to 6 electrons. So I need to make both of my half reactions exchanging 6 electrons, which means my top reaction here gets multiplied by 3, and my bottom reaction here gets multiplied by 2, and that will give me an exchange of 6 electrons. I'm going to rewrite both of these. I'm going to need to rewrite both of these because it's just going to get too messy otherwise. All right, so I'm going to rewrite my top reaction here. This is going to be 3 waters and 3 cyanides goes to 3CNO plus 6H plus 6E negative. So this is where it's really easy to make a simple mistake. And then you're unbalanced. So I'm trying to be really careful and make sure I multiply through properly. Okay, so now for my second half reaction. Again, this is 6E minus plus 2 times 4 is 8H plus 2MnO4 goes to 2MnO2 plus 4H2O. All right, just making sure that I've got everything multiplied through properly. Okay, so now at this point, because we've got the electrons balanced, we are going to add these 2 half reactions. And there's going to be some simplification that goes on here. So the first thing that I'm going to simplify is my electrons, of course, cancel or add out. But you can see, let me switch over to this. I've got 8H plus on the reactant side and 6H plus on the product side. I can simplify that. So the 6H plus is going to go away, and I'm going to be left with 2H plus on the reactant side. So again, this is a little bit like math when you're doing algebra. You can think about this like doing algebra, but algebra with atoms. And I can do some simplifying again with my waters. So I've got, waters on both sides. Again, I'm looking at where my arrow is, and sometimes it's helpful, I didn't do this here, to line up your arrows so that they're together, and then you can see a little bit easier what's on the reactant side and what's on the product side. But yeah, I can definitely simplify these waters. So my 3 waters are going to go away, and I'm just going to be left with 1 water over there. And I think that is all the simplifying that I can do. So let's add these half reactions. Okay, so now I have to be careful that I make sure I keep things that are on the reactant side and things that are on the product side on the product side. So my water is gone. Of course, my electrons are gone. I have 2H plus. Then I have 3 cyanide, and I have 2 MnO4. It's got a -1 charge, and now I go to the product side, and I have 3 CnO plus 2 MnO2. I'm totally out of space, so I'm going to have to squeeze my water in down here. So I just have 1 water. And again, just making sure that I have everything and I haven't dropped a molecule that I need. Okay, so, oh my goodness, it's already like the time just flies. So let's double check our atoms here. So starting, with my hydrogen, I have 2 hydrogen here and 2 hydrogen here. It's totally fine. 3 carbon and 3 carbon, nitrogen, 3 nitrogen, 3 nitrogen. Okay, so 2 manganese and 2 manganese. Let's check oxygen. So I have 4 times 2, I have 8 oxygen. So I get 3 here and 4 here plus 1 more here. That also gives me 8 oxygen. So my atoms are balanced. That's great. So let's double check our charges. So I have +2 minus 3. That gives me a -1 minus 2 more. So that gives me a -3. Maybe I should write this as a little side calculation. So +2 minus 3 minus 2. This gives me -3. All right, and then over here I have 3 times -1 is -3. Oh, and these two are neutral. Okay, so here I was expecting more of a calculation on the product side, but it's actually quite easy. So again, my charges are not 0, but my charges are equal. My charges are balanced. So now what I've got here is I have a balanced redox equation. Yikes. So I was going to do the next one and put it in basic solution, but there's no way I can get through that in 5 minutes. So what I'm going to do is I'm actually going to put this one in basic solution. Let's just put this one in basic solution. I'm going to need some space, so I'm going to take my little side calculations off there. Okay, so what I'm doing is I'm doing step 6A here. So I'm assuming that now I need to actually balance in basic solution. So if you need to balance in basic solution, you actually balance it in acidic solution first, and then you turn it into basic solution. And I'll show you how to do that. So what I'm doing is I'm neutralizing my acid by adding base. So because I have 2H plus here, I'm going to add 2 hydroxide. And that means now whatever I do on the reactant side, I have to also do on the product side. So I'm going to add 2 hydroxide to the product side. Now what this does is it takes this 2 hydroxide plus 2 protons, make 2 waters. So those 2 species come together, they neutralize, and they form 2 water molecules. So let me rewrite this. So now I have 2 waters plus 3 Cn minus plus 2 MnO4. That's also to a -1. I'm totally going to have to make this really small. I'm sorry, because I know it's better if I make it larger. O2 plus a water plus my 2 hydroxide. Like, oh, that's tiny. Sorry about that. Okay, so now I have switched this from acidic solution to basic solution, but actually I can simplify this one step further because I have 2 waters over here on my reactant side and I have 1 water on my product side. So I'm going to simplify it like I simplified the waters here, which means that this water goes away and this water just becomes 1. So I'm actually going to be able to fit things on here. So I'm going to erase that 2. That's become 1. And I get to erase this water molecule completely. And I'm just going to rewrite my 2 hydroxide a little bit bigger. Plus 2 hydroxide. So at this point, I now have a balanced redox equation in basic solution. So again, don't feel like you have to memorize a second set of rules for basic. Just go ahead and balance an acidic and then neutralize your acid by adding however much hydroxide you need. And again, very often when you do that, you'll find, well, you will form some waters. And so you usually end up simplifying waters kind of one more time in that situation. Okay, so yes, it is nearly 8 o'clock. I can't go through the other half reaction methods. I know I have had requests to do some acid base chemistry, so I will start doing acid base work next week. I think maybe the thing to do is to start with some definitions. What is an acid? What is a base? We can talk about things like autoionization of water. We can talk about conjugates. We can talk about the difference between weak and strong acids and bases, that kind of thing. If you want to go into calculations, maybe just depending on the time, we can do calculations of a strong acid or a strong base in aqueous solution, and then a weak acid and a weak base in aqueous solution. And then kind of the next natural thing to do is, okay, so what happens when you put an acid and a base together and you do a reaction? It's called a neutralization reaction, or sometimes it's called a titration as well. And we can do that as well. But just let me know. You can leave me a comment in this live stream. You can send me a message. You can send me a message on Facebook, on YouTube, whatever you want to do, and just let me know what is going to help you most in your class. So anyway, I hope you guys found this helpful, and thanks so much for joining me, and I hope to see you next week. Bye.